voltage swell, over voltage or under voltage condition. Yeah. Are you able to see this MATLAB file?
Yes,
Hello?
sir.
Yes, sir.
Yes, sir.
Yes,
Okay.
Yes,
sir.
sir.
So here first we understand that how to create a voltage sag and swell. Please all of you mute your mic, please. બધા પોતાનું mic છે mute કરી દેજો, please. Creates a noise here. So here we first simulate that how to create the sag and swell in MATLAB. Yeah? So here we have a three-phase system. So you can see that here left hand side we have a source, three-phase source, and second block that is a three-phase VI measurement block which measures the three-phase voltage and three-phase current. Yeah? And here we connect the three-phase loop. Here you can see that. Here we have three-phase loop. And here we measure the three-phase voltage VABC by using scope 1 and three-phase current IABC using scope. So how to create the sag and swell for over voltage and under voltage in three-phase system. Then after we understand that how to remove the sag and swell by using the DVR. Yeah? So here in the source, you can see that we have a parameters for the source. First is positive sequence component, which is a phase-to-phase RMS voltage amplitude. So here we take it is a 11 kV voltage, 11 e raised to 3. You can see that. Second is a frequency. So it is we take 50 Hz. Angle degree here we take 0. So start from the 0. Waveform start from the omega t is equal to 0. And here you can see that amplitude values variation. So here you can see that they ask that the variation on phase A only, but here we not click on this. Here we require the variation in all the three phases voltage, all the three phase quantity A, B, C, or you can see that R by B. So here amplitude values is given in per unit. So here first amplitude is 1, then is 0.5, then 1, 1.5 and 1. So this is the amplitude of voltage in per unit changes with respect to time. So here time value is given here. So here first time value is 0. It means at t is equal to 0 time, the amplitude value is this one. First per unit value 1 per unit is given. It means at t is equal to 0 time, the voltage, supply voltage provided by the source is 1 per unit, or you can say that it is a rated voltage. Clear? Next time 0.2 second, you can see that the amplitude of voltage in per unit changes from 1 to 0.5 per unit. So here it means that the source voltage is suddenly reduces to 50% of its rated value at time 0.2 seconds. It means that creates the voltage sag here. For how much time? So you can see that at 0.5 second here in time value, the amplitude value is become 1. This is a third value in amplitude is a 1. It means between 0.2 to 0.5 second, the source voltage is remains 0.5 per unit. It means 50% of rated value. At 0.5 second, it becomes 1 per unit, or you can say that it is a rated value. Fourth time, 0.7 second, the voltage becomes 1.5 per unit. It means that creates the voltage swell or over voltage condition at 0.7 second, and that is remaining up to remains up to 0.8 second, because at 0.8 second again the voltage amplitude becomes 1 per unit. So here by changing the amplitude here in this vector and by changing the time, you can make the voltage sag or voltage swell at any duration of the time. Clear? This is very simple. By just putting the time in which you require voltage sag or voltage swell, just put the time and corresponding the value for voltage sag or voltage swell in the amplitudes. So here you can observe that between between 0.2 to 0.5 second, your voltage remains 0.5 per unit. Clear? So between this duration 0.2 to 0.5, that creates the voltage sag, or you can say that under voltage condition. Same way, you can see that between 0.7 to 0.8 second, the voltage remains 1.5 per unit. So that creates the over voltage, or you can say that it is a voltage swell. So how to measure this? So that means measure by using this scope here. You can see that for that here we have VI measurement, three-phase VI measurement. So there's three-phase VI measurement, measure this three-phase quantity, voltage and current that we have measured here in scope 1 and scope 2. So here I run the simulation and observe that what is in the scope 1, three-phase voltage, and what is in scope 2, three-phase current. That creates voltage sag or voltage swell or not, as per the changes happen in the source. Here. So let's first compile this. After that, we open this scope 1 and scope 2. Yes, any doubt? Yes, anyone? So here simulation is run. Now we observe the scope 1, which gives the three-phase voltage. So you can observe this waveform. All of you see this screen? Scope 1 waveform.
Yes, sir.
Yes, sir.
So you can see that here in the x-axis there is a time, y-axis there is a magnitude. So you can see that between 0.2 to 0.5 second, the voltage reduces here. You can see that it is 0.5 per unit. Clear, all of you? Before the 0.2 second, or you can say that between 0 to 0.2 second, the voltage is 1 per unit, or you can say that it is a rated voltage. Clear? Same way, after 0.5 to 0.7 second, again the voltage remain normal, 1 per unit. But here at 0.7 second, we increase the magnitude in the source. It is 1.5 per unit. So that creates a voltage swell or over voltage. You can see here. The voltage between 0.7 to 0.8 second more than the normal rated voltage, or more than 1 per unit. It is a 1.5 per unit voltage. Clear? So here you can see that how to create the voltage sag and voltage swell at the load side by changing the supply block. So in actual practice, what happens that creates the voltage sag or voltage swell? So in actual practice is, suppose may be possible that two phases are short circuited. So that may be possible to create the voltage sag here, or some fault, open circuit fault, that creates a voltage swell or over voltage condition into the system. So here that we created by putting the values of magnitude of voltage with respect to time in the block of source. So I hope you clear that how to create the voltage sag and voltage swell. Clear, all of you? All of you clear this one? So
Yes, sir.
further I go to the next point, how to mitigate these two power quality problem, voltage sag and voltage swell, which is happen because of any fault in the transmission line or distribution line or from the power supply side. So here I have take the one simulation. So this is the simulation of single phase system with single phase DVR. All of you can see this screen. बताएं देखा ये?
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
So here you can see that here we have an AC source with peak amplitude 311. This is the peak value of the supply voltage. This is a single phase single phase transmission line. So here we have a single phase DVR, dynamic voltage restorer, to remove this voltage sag and swell. So here in this single phase circuit, first we understand that how this sag and swell is created. So another way you can create the sag and swell, that is by using this breaker. You can see that in this breaker, we have switching time. First switching time is 0.15 up to the 0.27 second. Clear? And see the initial status is 0. Initial status 0, it means that initially your breaker is in open circuit condition. Clear? It means that before this 0.15 second, here in switching time is between 15 to 27. It means that in this duration, this breaker is on, or you can say that it is closed. Clear? So it means between 0 to 0.15 second, this breaker is act as a open switch. Clear? So this breaker here used to create the voltage sag. So let's understand that how they create the voltage sag. So you first remember that between 0.15 to 0.27 second, here the status of this breaker become closed. So now understand that how they create the voltage sag into this single phase line. So here we have a voltage source. Here receiving side we have a load voltage. So across that we measure the voltage, that is called as a load voltage. Here we have an inductor, so that represents the transmission line. So here there is a breaker. So initially between 0 to 0.15 second, this breaker is open circuited. So current is flowing from supply to L1, from this capacitor, from load, and then negative of the supply. Clear? This is very easy. Again, repeat this. During normal condition, current is flowing from supply positive, inductor, from here capacitor, load, and negative. Because here breaker at that time is open circuit condition. So current is not flowing into this open path. Clear? So normal condition, this is the flow of current. So at that time, this voltmeter measures the voltage, that is called as V. So that V is nothing but a normal voltage under normal condition. So this voltage is nothing but your supply voltage. So whatever the supply voltage, same voltage is measured by this voltmeter. Clear? So this voltage we have measured here in the scope. This is the first parameter or first input in the scope. This is the voltage across the source. Clear? Now, at t is equal to 0.15 second, when this breaker is closed, up to this t is equal to 0.27 second, at that time, what will happen? Now the current is flowing from the supply, positive, inductor, L1, L2. Now this one is closed. So obviously current is flowing into this closed path. So current is going to this breaker because it is closed. Then it is into the loop. So it means that when this breaker is closed, that bypass the loop, or we can say that short circuit the loop. So when you measure the voltage between 0.15 to 0.27 second across the load side, that gives a zero voltage because your load is short circuited by this breaker. Clear? So of voltage sag. Now here this voltage not becomes completely zero because the capacitor is put here. So that maintains some voltage across the load, but that is below the rated value. So here this breaker creates the voltage sag between interval t is equal to 0.15 to 0.27 second. Now next, how to create the voltage sag. So here we have another breaker. You can see that here in this breaker, initial status is 0. It means normal condition, this breaker is open. So where it is closed, so here switching time is given that 0.037 to 0.43 second. It means in this interval, this breaker becomes closed. Here. So when this breaker is closed, you can see that in series with we connect the AC source and see the what is the magnitude of this AC source. This is a 500 volt. Clear? The peak value of this AC source is 500. Now let's see the main circuit diagram. So here our actual supply voltage how much? 311 voltage, 311 voltage. This is a peak value. But when voltage swell is happen, when this breaker is on in duration 0.37 to 0.37 to 0.43 second, when this breaker is closed, this AC voltage that come into series with the load, or that voltage come across the load. It means at the load side, now voltage is 500 kV. Sorry, 500 volt. This is the peak value, 500 volt. But actual system voltage is how much? At 311 volt. So it means that when this breaker is closed in duration of this 0.37 to 0.43 second, that creates the voltage swell across the load side. So when you measure the voltage here in this interval, the voltage across the load side is more than supply voltage. So that creates the voltage swell. Sorry, voltage swell over voltage condition. So how the current is flowing? So you can see that from the supply, positive. Here it is a connection of this breaker given here. So current is flowing from positive L1. This breaker is closed. So in series, 500 volt peak values come. Then that is connected here, the load side. So what you observe here load is bypassed, but how much voltage come across this terminal? So that is nothing but 500 volt, because in series with the breaker, we have connected 500 volt AC voltage source to create the voltage swell. Clear? So here we have two breakers. One breaker creates voltage sag. This breaker creates the voltage swell. So to remove this effect, voltage sag or voltage swell across the load side, we require the dynamic voltage restore. So you can see that here we have an inverter. This is a DC voltage source. We have a bridge inverter, so we have 4 switches. So here we have taken MOSFET as a switch. You can see that. And at the output side of this converter, we connect the series transformer, which connect the voltage in series with the line here. You can see that. This one is a positive terminal where we connect the inductor to limit the current. And here is the negative, or you can say that neutral wire. So there is a positive and neutral. Clear? So this is a positive terminal of transformer. This is a negative. This is positive and this is negative. Clear? So now how this DVR provide the voltage balance during voltage sag condition during interval 0.15 to 0.27 second, and how they provide how they absorb the reactive power during the voltage swell condition in the duration of 0.37 to 0.437 second. So here you can see the output of this inverter. Here we measure the voltage, which is nothing but a compensating voltage. So how this DVR provide the compensating voltage, and what is the magnitude of this compensating voltage? So that is measured by this voltage VC. That is nothing but compensating voltage. So that we have measured here in the second input into the scope. And third one is VL. This is nothing but a load voltage. So first, again I repeat, V is nothing but system voltage, which is measured here. VC is the compensating voltage, which is nothing but output of this converter. And VL is nothing but a load voltage. So this load voltage is nothing but a voltage you get after the compensation provided by this DVR. Here, see that here we measure the voltage before connection of DVR. So here in this voltage V, you not observe any compensation. If you see the simulation here result output, you see that in this V, There is no compensation because we connect the DVR after the measure of this voltage. After connection of DVR here between these two terminals, we measure the voltage across the load side here. So you can see the compensation in this load voltage VL. So first of all, we see the control circuit of this converter, how this DVR provides the control circuit, control signal to this 4 switches or this 4 MOSFET to generate this compensating voltage and provide the voltage regulation at the load. So here we take this V. This is nothing but the voltage. This one measured before the connection of this DVR. So that is applied to this reference voltage generator or reference voltage calculation. So this V, that is act as an input for the PLL. So first we understand that what is PLL. So it is nothing but a phase lock loop which is used for the synchronization of the fundamental voltage with the output voltage. Whatever you provide the compensation, that compensating voltage must be synchronized with the reference voltage. Clear? So for that we require this phase lock loop. So that provides the automatic gain control system. So here this regulator gains, you can see it as 180, 3201. So that is a optimal value of the gain for which they provide the regulation of the voltage. And here you enable this automatic gain control. So that automatically controls the value of gain and provides a regulation at the load side near to the 1 per unit voltage. So here the different parameters in this PLL block: minimum frequency, so how much variations you observe at the receiving side. 49 frequency here you take, or you can take also 50 Hz. How much frequency of your supply? So here we have 50 Hz, so here put the 50 Hz. If your supply is 60 Hz, so put 60 Hz here. This is a regulator gain. This is the optimal value. You can see that here is right that for optimal performance, set the regulator gain Kp, Ki and Kd 180, 3201. So that's why we put here. So that provides the optimal regulation. And check the enable automatic gain control parameter. So that's why here we enable it. So what is the input of this PLL block? That is nothing but normalized input signals. So here we have V. This is the normalized input signal in per unit. So what is the output of this PLL block? So output 1, that is nothing but a frequency. So that frequency in Hertz. Output 2, that is nothing but omega t or 2 pi. That is in synchronization with the zero crossing of the fundamental input signal. So this omega t angle that is synchronized with this V voltage. Clear? It means when the V voltage this cross the zero crossing, at that time this angle also becomes zero crossing. So here the output of this PLL block is angle omega t. So that angle is applied to the sine function, trigonometric function. And that sine omega t multiply with the peak value. Here our peak value of the supply is 311. So this product that gives Vm is nothing but 311. Vm sine omega t. Omega t is we get from this PLL. So this Vm sine omega t voltage subtracted from this voltage V, and whatever the error between this voltage Vm sine omega t and V, that is act as a reference voltage for the controller. So now this reference voltage is again subtracted from the compensating voltage. You can see the output of this reference voltage calculation is VR, which is subtracted from this VC. So VC is what? That is a compensating voltage. Suppose that right now at t is equal to 0 normal condition, this compensating voltage is 0 because there is no compensation is required, because at the load side voltage is same as the supply voltage or rated voltage. So there is no compensation is required. Clear? But when the voltage sag is happens, at that time you require the voltage compensation. Clear? So at this time, at the starting, this VC is 0. So this VC is subtracted from this VR. So initially period, when you not provide the compensation, it means at t is equal to 1 5 second, when the voltage sag starts. So at that time you require the voltage compensation. So at this time, what is the output of this summation? Initially VC is 0 and reference voltage calculation generate the voltage VR reference. So that output is VR. So if this output VR applied to the relay circuits. So here in the relay, we provide the threshold value, positive and threshold and negative threshold. So here for switch on of this relay or to turn on this relay, positive threshold applies 0.1. It means that here if the input of this relay is more than 0.1, then this relay is on. Clear? Same way, if the input of this relay is more than minus 0.1, at that time this relay is open. Clear? So this is the threshold is given for positive and negative value. When it is more than 0.1, it is switch on. It means it is act as a closed switch. If it is more than minus 0.1, then it is open. So let's now see that. Suppose that here VR is 0.3 value. Reference value is 0.3. At initially time VC is obviously 0 because we not provide compensation at 0.15 second. So output is 0.3. So it is more than 0.1. It means the relay is closed. Now, when relay is closed, its output is 1. You can see that output is 1 when it is on. So output of this relay is on. So that one output is applied to the gate pulses of this both the MOSFET Q1 and Q4. It means that you apply the gate pulses to this MOSFET Q1 and Q4 when the output of relay is 1. Here through this not logical operator, we provide the gate pulses to MOSFET Q3 and Q2. So here when relay output is 1, so obviously the gate pulse is provided to this Q3 and Q2 is 0. It means both these MOSFET act as an open switch. Only Q1 and Q4 is on when relay is on. So now how the current is flowing? So from this DC supply, positive Q1 is on because of gate pulse is applied 1. Then through this inductor, this is a positive polarity. Primary of the transformer, negative Q4 and negative of the supply. So by this way, the current make the closed path. So by this way, during the relay on condition, this controller inject the voltage in series with the line. Clear? Because that is a positive value. Because current is flowing in the positive direction. Suppose assume exactly opposite. Suppose the value of this output relay is 0.3. Sorry, input of this relay is 0.3 minus 0.3. So it is a threshold of switch off period. Clear? It means that your relay is off condition. So when relay is off condition, output is 0. You can see that output when off is 0. So when output is 0, through this not logical operator, so output or gate pulse is provided to the MOSFET Q3 and Q2. And at that time, gate pulses for Q1 and Q4 is 0 because output of the relay is 0, which is directly connected to the gate of Q1 and Q4. So at this time, your Q1 and Q4 is act as a open switch and Q3 and Q2 act as a closed switch. So how the current is flowing? From positive of the supply, Q3, from this terminal of the transformer, inductor, Q2 and negative. So this is the negative polarity of the primary voltage, same polarity at the secondary side. So that injects the negative voltage. Clear? Inject the negative voltage means that they absorb the reactive power from the system during the voltage swell condition. So when this swell is happened between 0.37 to 0.43 seconds, at that time, they provide the negative voltage, or you can say that they absorb the required amount of reactive power. So let's understand that through this simulation, through this waveform, how they provide the compensation. Again, keep in mind that voltage sag happens between 0.15 second to 0.27 second by this breaker. and between t is equal to 0.37 to 0.43 second, that generate the voltage swell by this breaker, because in series we have connected 500 volt AC voltage source. Clear? So let's observe the waveform. First is the V voltage. This is the voltage before the DVR. VC is the compensating voltage provided by the DVR here, and VN is the voltage across the load after the DER. So it means that load voltage with compensation. So let's see the waveform of it. So here, all of you can see the screen.
Yes, sir.
Okay. So you can see that first is the V, which is the load voltage, but without compensation, because that we have measured before the DVR. You can see that. This V we have measured before this DVR. So that in that DVR we have not seen the compensating voltage. So initial time between 0 to 0.15 second here up to this point, the voltage measured by this voltmeter is same as the supply voltage. Clear? With peak value 311 volt, because there is no any voltage power quality problem between the duration 0 to 0.15 second. Clear? So at this time you can see the compensating voltage which is generated by the DVR. It's this voltage, output of this converter. This voltage is given in the scope 2, second reference line. So between 0 to 0.15 second, it is 0. Why 0? Because your load voltage is same as your supply voltage. So there is no power quality problems like voltage sag or voltage swell. So there is no requirement of any injection of voltage or absorption of the voltage to the reactive power through this DVR. Clear? So that's why the compensation provided in that duration of time is 0. Clear? It means that in this duration your DVR is off condition. Clear? Now you can observe this waveform load voltage at 0.15 second here, between 0.15 second to 0.27 second here. The voltage is reduces. Why? Because through this breaker 1 we have created the voltage sag. Clear? Because we short circuit the load. Clear? So that's why this voltage is reduces here, because that bypass the load. So you can observe that the load voltage is reduces below the its rated voltage, or we can say that below the supply voltage. So this is a condition of voltage sag in the duration 0.15 to 0.27 second. Now at this time you see the compensating voltage. Now your DVR is operated because the sense that at the load side voltage becomes below the rated voltage. So we need to inject the voltage to make the voltage near to the 1 per unit or rated voltage. So to make the load voltage per units, the DVR inject the required amount of reactive power or required amount of voltage in series with the line to maintain the load voltage near to the 1 per unit. So you can see the waveform 3. This is nothing but a load voltage with compensation. That voltage we have measured here, load side. So this is connected after the compensation. So in this voltage, we have not observed any voltage variation. Why? Because here this DVR inject or absorb the reactive power, or by injecting voltage or absorbing the voltage, they maintain the voltage at the load side near to the supply voltage or rated voltage. So that's why here in the VL load voltage do not observe any variation. You can see that here at 0.15 second, when voltage, supply voltage is reducing, so not supply voltage but load voltage without compensation, that is reduces. But here because of providing the compensation after 0.15 second, the load voltage is maintained its rated value. You can see that it is 311 per unit. So 311 voltage. Clear? Or you can say that it's a 1 per unit. Clear? So there is no voltage deviation between 0.15 to 0.27 second, because this DVR inject the voltage in series with the line. So one thing here you observe that how they inject the voltage in series with the line. So here we require the more voltage as compared to the actual load voltage. So that compensation provided by this compensator, which is positive. So it means that when here this load voltage is positive, that means positive voltage cycle starts, at that time that compensator or this converter injects the positive cycle of voltage. So that boosts up the voltage at the load side. So a positive cycle of the load voltage, they inject the positive voltage of required value to maintain its per unit. Same way during the negative value of negative voltage or negative half cycle of the supply voltage, they inject the negative voltage to maintain the minus 311 voltage peak value. Clear? So that inject in series with the line during voltage sag condition. Clear? So I hope you understand that during voltage sag condition how your DVR will operate. All of you clear up to this? All of you clear?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Yes, sir. Now let's understand that voltage swell condition. So first see that where voltage swell is happen or overall voltage happens between 0.37 to 0.43 second. Clear? So let's see that in the waveform between 0.37 to 0.43 second. Where is 0.37? Here. After this 0.3 second here. Clear? So sorry, here 0.37 here. This is 0.35 second. So here you can observe that the load voltage without compensation, that is more than the rated voltage or more than 311 peak voltage. You can see here at 0.37 second up to the 0.43 second. So this three waveform, you can see that in 3 cycle that creates the voltage swell because breaker is closed. So in series you connect the 500 watt peak value. So that creates the voltage swell condition or over voltage condition at the load side. Now at this time, this compensator compensate by injecting the voltage. Keeping in mind that here word inject the voltage, but you see the phase of this injection of the voltage. You can see that in the positive cycle of the load voltage, you can see here that inject the negative voltage, because now at this time voltage at the load side is more than the rated voltage. So we need to reduce the voltage. So to reduce the voltage, we inject the negative voltage to make the voltage at the load side 1 per unit. So that's why here injection of the voltage is out of the phase of the load voltage. Exactly 180 degree phase shift with your normal load voltage. So here during the positive cycle of the load voltage, this compensator injects the negative voltage. Clear? Required amount of negative voltage, which makes the voltage at the load side 311 peak or rated voltage. Clear? Same way in the negative cycle of the load voltage, they inject the positive voltage. You can see that. Negative cycle of load voltage that inject the positive voltage. This. Clear? So you can see that there is no variation in the actual load voltage here in this cycle. So throughout this time, during voltage sag condition or voltage swell condition, there is no variation in the load voltage because here we provide the compensation by using this compensator. So this second waveform is nothing but a compensating voltage provided by this DVR. Clear? So after 0.43 second, you can see that here. After 0.43 second, what will happen? Again, your system or load voltage becomes normal. You can see the first voltage or first waveform. Your voltage becomes normal here with peak of 311 voltage. So at this time, compensating voltage again becomes 0 because there is no need of compensation because your load voltage is same as the supply voltage. So there is no need of compensation. It means your DVR is off at this time. So VC or compensating voltage is 0. Here. So throughout this operation, during voltage sag condition between 0.15 to between 0.27 second, there is no variation in the load voltage. Same way here between 0.37 second to 0.43 second, there is no variation in the voltage across the load side. So this is the operation of DVR and how to simulate this DVR in the MATLAB. You can see that this is a single phase DVR with series compensation. The same way the UPFC also works. So only difference is that between UPFC and DVR is that for this particular problem, voltage sag and voltage swell condition, UPFC works for the transmission line and DVR is used for the distribution line or low voltage line. Here, but the operating principle of both the FACT devices are same. So I hope it is clear to all the modeling of DVR in MATLAB, how to create the voltage sag and voltage swell in single phase circuit. One way to create the sag or swell by using the breaker. You can see here in this circuit. Second way to create the voltage sag and swell by changing the magnitude of source voltage here in three phase. You can see that. Or you can also simulate voltage sag and swell in three phase circuit by using the three phase breaker. By the same way as we have done here, this DVR. Here, three phase breaker is also available in the MATLAB. So by using this three phase breaker also, you can create the sag and swell in three phase circuit. Here. So I hope it is clear the operation of DVR to remove the power quality problem like voltage sag and swell and how to simulate this in MATLAB and how this controller works. The main logic is here in this control circuits, PLL, phase lock loop. So I hope it is clear to all of you. If you have any doubt, you can ask me right now.
Sir, can you explain that graph after 0.37?
Graph after 0.37. 1 minute.
Yes, sir. I'm in the voltage swell condition.
Okay. 1 minute. 0.37 second. After 0.37 here.
Yes, sir.
Yes.
Yes, sir. Sir, screen is getting visible here.
देखा है बताना?
Yes, sir. Now
Yes.
it's visible.
So at 0.37 time, 0.37 second, what will happen? Voltage swell. Here. You can see that here in the simulation by using this breaker. This breaker is closed at 0.37 second. You can see here. Closed between 0.37 to 0.43 second. So when it is closed, this AC voltage come in series. And this AC voltage value is 500 peak value. This is more than the supply voltage. Supply voltage is 311 peak. Clear? So
Yes.
you can observe that after 0.37 second, the voltage, it becomes more than the normal rated voltage. So here you can see that before 0.37 second, here is the 0.37 second. Before that, the load voltage is normal, 311 peak. Clear? Or you can say that 311 Vm sin 311 sin omega t variation, RMS value. Clear? At 0.37 second, when you close the breaker, when series 500 volt come in series, that creates the voltage swell. Because the voltage at the load side becomes more than the normal rated voltage. Clear? So between 0.37 to 0.43 second, the voltage is more than your supply voltage. Or you can say that it is a condition of voltage swell or over voltage condition. Clear? So at this time, what we require? To maintain the voltage at the load side rated value? Yes or no?
Yes, sir.
So how to make the rated voltage? So by reducing the voltage at the load side and make it at a near to the 1 per unit. By this way, we can make it to the normal value. Because what will happen when over voltage happens, voltage swell happens, sudden rise of the voltage at the load side, may be possible that your load will be damaged. Clear? So voltage swell as well as voltage swell both are harmful to your load. So in this condition, you require the injection of voltage in series with the line, but with the out of phase, exactly 180 degree, because you want to decrease the voltage. How much voltage you want to decrease? So here you can see that 500 peak voltage, your actual system voltage is 311, so it is almost 200 volt. Clear? So you inject the 200 volt in series with the line, but with exactly 180 degree phase shift. So you can see that here in the first positive cycle of this voltage swell with 500 voltage peak, the compensating voltage provided by this DVR, that is exactly opposite of its phase. It means this is a negative value. This is a reference line. So this is a negative value, which is almost, you can see that it is a 200 volt, minus 200 volt. You can see here. Clear? So by injecting the minus 200 volt in series, we can make the voltage at the load side near to the rated or with the peak of 311 volt. Clear? So that's why during this interval, we inject the voltage in series with the line with exactly 180 degree out of phase as compared to the load voltage. I hope it is clear to you.
Yes, sir.
Same way in the voltage sag condition, our voltage is lower than the rated voltage. So we need injection of voltage such a way that our voltage remains 1 per unit. So here you can see that our voltage is in the voltage sag condition, it is around 100 volt. Clear? So how much voltage is required to make this voltage near to the 1 per unit? Almost 200 volt. Clear? So here we require increase of the voltage. So that's why we have injected the voltage in series with positive value without any phase shifting. So here when supply voltage is positive, so here compensating voltage is also positive. And this magnitude is, you can see that it is around 200 volt. So it is 200 volt plus this 100 volt. So how much? It is 311 peak. Clear? And maintain the voltage at the load side. You can see that here in the third waveform, it is rated value. I hope it is clear to all of you.
Yes, sir. Clear.
All of you clear? Any doubt? So this is a simulation of DVR. You also see the one video. I have given this video to you already in the, I think, third or fourth lecture regarding the operation of DVR. I hope you have see this video. Did I enjoy the video? How this DVR works? This is the hardware model of DVR. How they inject or absorb the voltage.
Yes, sir. You have shown us.
Yes. Okay. So all of you understand this video, how this DVR operates in hardware model? Can I explain again it? Can I explain or you understand this?
Sir, explain that.
Okay. So here, this is the hardware model of single phase DVR. You can see that here we have supply. This is a P positive and this is a neutral single phase voltage. Here we have a DVR in which we have two controllers, because here we not have a fixed DC voltage. In the simulation, we have take the capacitor as a DC source, but here we have not a source voltage, DC source voltage. So for that, we have used the one converter, which is called as a rectifier. So this rectifier, these four switches, is a bridge type of rectifier. Input of this bridge rectifier is this single phase source. we convert this AC into DC and then store the charge into this capacitor. And whenever it is required of injection, that capacitor provides this power to these inverters. Clear? So that inverter output that is injected in series with the line through this series transformer to make the voltage at the load side 1 per units. Here filter is used because of switching in the inverter that creates the harmonics. So to remove this harmonics, here before injection of this voltage, we provide the filtering to remove the harmonics. So here only difference between modeling of DVR in the MATLAB and this DVR is that in the modeling of a DVR in the MATLAB, we have not used this converter because we have a fixed capacitor as a DC source. In the hardware model here, we generate the DC source by using this rectifier. Here we take the source from the single phase source. So assume that this is a single phase transmission line. You can see that. And here receiving side, you connect the load. Clear? And you can see that DVR, both the converter, rectifier, inverter, operated by this DVR control units. So this is nothing but a controller that provides the control gate signal, all the switches. And you can see that here are the test point is given. So from this test point, you can measure the gate bus in the CRO. And from here, these terminals V in, you can measure this input voltage. Here V output, you can measure this output voltage across the load side. Clear? And here this is a main control switch from which you had turn on this DVR, and you can measure the AC voltage from here. This multimeter, this meter, analog meter, which is used to measure the voltage, supply voltage. Generally, we give the voltage in the range of here 170 to 270, and when the voltage sag is happen here in this condition, in this circuit. So first of all, the question is come in mind how to create the voltage sag and swell here in this hardware model. So here same way like simulation, we change the supply voltage. Here in this hardware model that is designed for the rated voltage near to the 220 volt. Here. So here at the load side, we maintain the voltage near to the 220 volt. 220 volt is a rated voltage. Here. So here from the input side, we can vary the voltage between 170 to 270. It means by vary the voltage from the supply side through the variac, you can see that here left hand side, we have variac. From that, we can vary the voltage between 170 to 270. So if our voltage is below 220 volt supply side, it means that creates the voltage sag at the load side. Clear? Obviously, if your supply voltage is less than 220 volt, so obviously at the load side, your voltage is less than 220 volt. So that creates the voltage sag condition or under voltage condition. Same way, through this variac, you can increase the voltage more than 220 volt. So through this variac, suppose I increase the voltage 250. Clear? So here at the load side, I get the voltage around between 240 to 250 because of some loss between the line. So again, your normal voltage is what? Rated voltage is what? 220. Clear? So that is a over voltage condition or voltage swell condition. So both this condition, voltage sag and swell, that is created from here source by changing the voltage through this variac. Clear? Now, same logic here. Suppose the voltage sag is created. Suppose my voltage is here. You can see that in the screen it is 190 voltage. Here you can see that in the digital screen, the output voltage at the load side is 190 volt. Clear? It means that is a voltage sag condition. I require the load side 220 volt. So extra 30 volt is provided by this controller. Okay. So here this rectifier takes the power from this source, convert to DC, start this capacitor, and here during the voltage sag condition, this inverter is operated. So how this inverter know that how much voltage is injected? So for that, this control circuit provides this control signal. You can see that 4 gate pulses for all these 4 switches is provided by this control circuit. So this is the input of this control circuit. You can see that input voltage. This is the input voltage. What is the input voltage given from the source? And what is the output voltage? And what is the synchronized voltage? What is the reference voltage? So all these parameters is given to this control circuits. Same like a simulation in which we see that PLL blocks that generate the control signal or reference signals, based on that provide the firing pulses to the controller. Here, same way in same control circuit here in this controller, based on the requirement of the voltage, by sensing the load voltage and supply voltage, that generate the gate signal in such a way that at the output side of this inverter, we generate the required voltage. So here in this case, that generate the near to the 30 volts, filter out it and inject into the series with the line. Here, how they injects? So that injects in the phase with the supply voltage, because here we want to increase the voltage. So whenever your supply voltage is positive, at the same time, the positive voltage of this 30 volt is injected. So that makes the voltage at the load side 220 volt or rated voltage. Exactly opposite in voltage swell condition. So I think clear to all of you how this DVR is operated. All of you clear?
Yes, sir.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So if you have any doubt, you can ask me. Right now, I give you 1 or 2 minutes. If you have not any doubt, so here we have stopped this lab session.